At around the same time, larger telescopes were being built that were able to accurately measure the spectra, or the intensity of light as a function of wavelength, of faint objects. Using these new data, astronomers tried to understand the plethora of faint, nebulous objects they were observing. Between 1912 and 1922, astronomer Vesto Slipher at the Lowell Observatory in Arizona discovered that the spectra of light from many of these objects was systematically shifted to longer wavelengths, or redshifted. A short time later, other astronomers showed that these nebulous objects were distant galaxies. The discovery of the expanding universe. Meanwhile, other physicists and mathematicians working on Einstein's theory of gravity discovered the equations had some solutions that described an expanding universe. In these solutions, the light coming from distant objects would be redshifted as it traveled through the expanding universe. The redshift would increase with increasing distance to the object. Edwin Hubble. In 1929, Edwin Hubble, working at the Carnegie Observatories in Pasadena, California, measured the redshifts of a number of distant galaxies. He also measured their relative distances by measuring the apparent brightness of a class of variable stars called Cepheids in each galaxy. When he plotted redshift against relative distance, he found that the redshift of distant galaxies increased as a linear function of their distance. The only explanation for this observation is that the universe was expanding. Once scientists understood that the universe was expanding, they immediately realized that it would have been smaller in the past. At some point in the past, the entire universe would have been a single point. This point, later called the Big Bang, was the beginning of the universe as we understand it today. The expanding universe is finite in both time and space. The reason that the universe did not collapse, as Newton's and Einstein's equations said it might, is that it had been expanding from the moment of its creation. The universe is in a constant state of change. The expanding universe, a new idea based on modern physics, laid to rest the paradoxes that troubled astronomers from ancient times until the early universe. In the late 1940s, American physicists George Gamow, Robert Herman, and Ralph Alpher realized that long ago, the universe was much hotter and denser. They made calculations to show whether nuclear reactions that took place at those higher temperatures could have created the heavy elements. Unfortunately, with the exception of helium, they found that it was impossible to form heavier elements in any appreciable quantity. Today, we understand that heavy elements were synthesized either in the cores of stars or during supernovae, when a large dying star implodes. Gamow, Herman, and Alpher did realize, though, that if the universe were hotter and denser in the past, radiation should still be left over from the early universe. This radiation would have a well-defined spectrum, called a blackbody spectrum, that depends on its temperature. As the universe expanded, the spectrum of this light would have been redshifted to longer wavelengths, and the temperature associated with the spectrum would have decreased by a factor of over 1000 as the universe cooled. The cosmic microwave background radiation. In 1963, Arno Penzias and Robert Wilson, two scientists in Holmdel, New Jersey, were working on a satellite designed to measure microwaves. When they tested the satellite's antenna, they found mysterious microwaves coming equally from all directions. At first, they thought something was wrong with the antenna. But after checking and rechecking, they realized that they had discovered something real. What they discovered was the radiation predicted years earlier by Gamow, Herman, and Alpher. The radiation that Penzias and Wilson discovered, called the cosmic microwave background radiation, convinced most astronomers that the Big Bang theory was correct. For discovering the cosmic microwave background radiation, Penzias and Wilson were awarded the 1978 Nobel Prize in Physics. After Penzias and Wilson found the cosmic microwave background radiation, astrophysicists began to study whether they could use its properties to study what the universe was like long ago. According to Big Bang theory, the radiation contained information on how matter was distributed over 10 billion years ago, when the universe was only 500,000 years old. At that time, stars and galaxies had not yet formed. The universe consisted of a hot soup of electrons and atomic nuclei. These particles constantly collided with the photons that made up the background radiation, which then had a temperature of over 3000 C. Soon after, the universe expanded enough, and thus the background radiation cooled enough, so that the electrons could combine with the nuclei to form atoms. Because atoms were electrically neutral, the photons of the background radiation no longer collided with them. When the first atoms formed, the universe had slight variations in density, which grew into the density variations we see today, galaxies and clusters. These density variations should have led to slight variations in the temperature of the background radiation, and these variations should still be detectable today. Scientists realized that they had an exciting possibility. By measuring the temperature variations of the cosmic microwave background radiation over different regions of the sky, they would have a direct measurement of the density variations in the early universe, over 10 billion years ago. Density variations in the early universe. Map of the sky is observed by COBE. The map on the bottom shows the temperature variations of the background radiation. In 1990, a satellite called the Cosmic Microwave Background Explorer (COBE) measured background radiation temperatures over the whole sky. COBE found variations that amounted to only about 5 parts in 100,000, but revealed the density fluctuations in the early universe. The initial density variations would be the seeds of structure that would grow over time to become the galaxies, clusters of galaxies, and superclusters of galaxies observed today by the Sloan Digital Sky Survey. With the Sloan data, along with data from COBE, astronomers will be able to reconstruct the evolution of structure in the universe over the last 10 to 15 billion years. With this information, we will have a deep understanding of the history of the universe, which will be an almost unbelievable scientific and intellectual achievement. But measuring the evolution of the density variations in the universe still does not answer the most important question: why does the universe contain these differences in density in the first place? To answer this question, astronomers and astrophysicists must understand the nature of the density variations and construct theories of the origin of the universe that predict how these variations should occur.